Today we're going to look at a pretty interesting inequality which I found on the Math Stack Exchange. So here's the number if you'd like to check it out. And the solution strategy that I took is also from a post there. So again, make sure to check that out if you'd like to see it. I filled in some of the details, however. So our goal is to show for all positive x, y, and z, we have x to the x over x plus y to the y over y plus z plus z to the z over z plus x is bigger than or equal to 3/2. So let's notice here we have a cyclic sum. And what I mean by that is we start off with one term and we produce the second term by replacing x with y and y with z. And then we move to the third term by replacing y with z and z back with x. And then it would loop back on itself if we were to do another replacement. So I think what makes this inequality interesting and also a little bit tricky is the fact that we've got variables in the base and the exponent. And that always makes calculations a bit tricky. Okay, so we're going to use two lemmas or two simpler inequalities to prove our final statement. And we'll prove these two lemmas for the case when x is positive, although the first one is true for all real numbers x. First, we'll show that e to the x is larger than x plus 1. So I've put this with a blue dot, so I'll bring this up here with a blue dot as well. And I think there's a very obvious way to do this with Taylor series, although I won't do it with Taylor series, I'll do it with a function. And that's because this method would extend to this orange, this actually true for x in real numbers if you're careful. Okay, so anyway, let's get into it. So let's consider the following function. I'll call it f of x, and it will be e to the x minus x minus 1. And let's note, in order to prove this lemma, what we'd like to show is that f of x is bigger than or equal to 0 for all x bigger than 0. So that would establish our inequality. Okay, nice. So let's start with the following observation. So I'll just put note here that f of 0 is equal to e to the 0 minus 1, but that's equal to 1 minus 1, which is 0. Okay, so we start off with our function is equal to 0. But after that, we'll show that it's always increasing. And if it's always increasing from 0, that means it's always positive. So how can we show that it's always increasing? Well, with the first derivative test. So let's take the first derivative. That will give us e to the x minus 1. And how do we find out where that's positive and thus the original function is increasing? Well, we find out where it's equal to 0. So notice that it's equal to 0 exactly when e to the x is equal to 1, but that's exactly when x is equal to 0. So that's the only place that the first derivative is 0. So all we have to do is pick some number bigger than 0 as a test point. So maybe we'll pick the number 1, for instance, and look, f prime of 1 is equal to e to the 1 minus 1, but e is approximately 2.718. You subtract 1, you definitely get something bigger than 0. In fact, you get something bigger than 1, which is bigger than 0. So this means we're increasing at 1, but since we're increasing at 1 and the only place it can change from being increasing to decreasing is at 0, that means that we're increasing for all x bigger than 0. So in other words, we have f prime of x is bigger than 0 for all x bigger than 0. Okay, so let's see what we have. We have f of 0 is 0. And then we have f is increasing after 0, but putting those two things together, so let's do a little bit of color coding. Maybe you have an orange dot here and an orange dot here. So those two orange dots will imply that f of x is bigger than or equal to 0 for all x bigger than or equal to 0. But that's a little bit stronger than we wanted to prove because this includes 0 over here, but our original inequality did not. Let's move on to our red dot inequality, which says x times the natural log of x is bigger than or equal to x minus 1. In order to prove this, we'll do the same sort of thing. So let's set g of x equal to, let's see, in this case we'll want it to be x times the natural log of x minus x plus 1. And in order for this inequality to hold, what we will want to show is that g of x is bigger than or equal to 0 for all x bigger than 0. Okay, so that's good. So let's notice that something is going on at x equals 0. In fact, that's not in the domain. In fact, no negative numbers are in the domain either. The domain here is, in fact, just positive values of x. So we kind of have to figure out what's going on very close to x equals 0 from the right. So let's maybe write that as follows. So let's notice that g of 0 from the right, and by that I mean the limit as x goes to 0 from the right of g of x is equal to, well, let's notice that's the same thing as the limit as x goes to 0 from the right of x times natural log of x plus 1. We're able to get rid of this minus x because the limit of that is very clearly equal to 0. Okay, but then this is an indeterminate form of type 0 times infinity, so we could use L'Hopital's rule after rewriting it a little bit. This is the limit as x goes to 0 from the right of the natural log of x over 1 over x, and then plus 1. But then applying L'Hopital's rule, and I'll actually skip a step here, we'll see that this limit goes to 0, adding 1, we get the number 1. So maybe summarizing that right here in this orange box, we have our quote-unquote value of g of 0 from the right is equal to 1. So it's positive. Okay, so that's important to know. There's actually another value of g of x which will be important as well, and that is g evaluated at 1. So let's notice g evaluated at 1 will give us 1 times natural log of 1. Natural log of 1 is 0. And then minus 1 plus 1, so this gives us 0. Okay, great. So let's keep in mind those two values. And now let's investigate the derivative. So let's take the derivative of g of x. So what will we get there? So using the product rule on this first term, we'll have the natural log of x plus x times 1 over x, and then we have to subtract 1 from the derivative of x. But notice x times 1 over x is 1, so those cancel, giving us the natural log of x. So now let's notice that this branches off into two cases depending on whether or not x is less than 1 or bigger than 1. So let's first look at the case when x is between 0 and 1, and we'll see that this is negative. So let's just write here, it's negative. I could write that it's less than 0, but we'll write that it's negative. But if the derivative is negative, then the function is decreasing. So we'll keep that in mind. But then if x is bigger than 1, so in other words, it's on the interval from 1 to infinity, this derivative is positive, which means our function is increasing. Okay, so now let's put this information together with these two values to see that we have indeed satisfied this inequality right here. So we can't really graph this perfectly, but we can get an idea of the sign very quickly. Okay, so let's notice g of 0 from the right is equal to 1. So we have a 1 right here. And then we have g of 1 is 0. So we have g is equal to 0 right here. Great. And then we know between 0 and 1 it's decreasing. It's decreasing the whole time between 0 and 1. But if it's decreasing the whole time between 0 and 1, then it's impossible for it to cross the x-axis. Because if it were to cross the x-axis somewhere between 0 and 1, then in order to get back to the x-axis, it would have to increase. But that's been contradicted by our calculation over there. So that means we're decreasing like this. Okay, and like I said, we don't know exactly what the curve looks like, so we'll just sketch something. And then after 1, the derivative is always positive. So it's always increasing in this direction. So it's going something like that. But notice that because of those constraints, we have the graph of our function g of x is always above the x-axis. But since it's always above the x-axis, that means it's always positive like this right here. But since it's always positive, we know that our inequality over here is satisfied. So now we have these tools in place. Let's look at our goal inequality. So we're going to look at something that looks like one of these terms first, and after doing that we will put it all together. And I don't want to use up x and y and z just yet, so maybe I'll use the variables a and b. So let's consider, like I said, a and b, which are bigger than 0. Great. And now let's look at the square root of a to the a times b to the b. And let's rewrite this a little bit. So we'll take the square root and rewrite it as something to the 1/2 power. And then we'll take the a to the a and the b to the b and rewrite it using the natural base. So we can write the a to the a as e to the a times natural log of a, using exponential and logarithm rules. And then similarly, b to the b can be written as e to the b times natural log of b. Great. But now we can smush those two together. That gives us e to the a natural log of a plus b natural log of b, all to the 1/2 power. But now we can bring that 1/2 inside, and we'll have e to the a natural log of a over 2 plus b natural log of b over 2. But now what are we going to do now? Well, notice we've got a natural log of a and b natural log of b. That motivates us to use this second inequality that we derived. Okay, so let's put an inequality here. And together with that inequality, maybe we'll put an arrow and a red dot to show that we're coming from this red dotted inequality over here. I guess it's also important to point out that the exponential function is an increasing function, which is another reason why we can do this. Okay, so let's see what we have. We'll have e to the a minus 1 over 2 plus b minus 1 over 2. So again, that's just a direct application of our inequality over here. But what does that simplify to? It simplifies e to the a plus b over 2 minus 1. Okay, good. But now we can apply our blue dotted inequality where x is this a plus b over 2 minus 1. So let's do the same thing with our color coding. So here we'll have this blue arrow and this blue dot to show that we're using from this blue dotted inequality. And this is going to be bigger than or equal to a plus b over 2 minus 1 plus 1. The minus 1 and the plus 1 cancel and we get a plus b over 2. But now let's read this from the extreme left and right hand side and see if we can rewrite it at all so that it looks close to one of these terms. And we can. Maybe a first step to do that would be to notice that the square root of a to the a times b to the b over a plus b is bigger than or equal to half. That's one step. But then if we'd like to turn this into just a to the a in the numerator, we'd have to multiply by something. And what will we multiply by? Well, we'll multiply the whole thing by the square root of a to the a over b to the b. So let's see what that'll leave us with. Then we'll have a to the a in the numerator over a plus b in the denominator. And then we'll have a 1/2 square root of a to the a over b to the b on the right hand side. Okay, so now let's bring this up here and then we'll finally finish it off. So far we've derived the following inequality, which in itself is pretty awesome. So for all a and b which are bigger than 0, we have a to the a over a plus b is bigger than or equal to 1/2 times the square root of a to the a over b to the b. Now we're ready to put this all together. So let's start with our left-hand side. So I'll just copy that over. So this is going to be bigger than or equal to, well, I can take a half out of the whole thing, and then I'm left with this sort of radical expression for each of these. So let's see, we'll have the square root of x to the x over y to the y plus the square root of y to the y over z to the z plus the square root of z to the z over x to the x. So I have something like that. Now from here I'm going to use something called the arithmetic geometric mean inequality. So let's recall what that is. So the AMGM mean inequality. So that will say that A plus B plus C over 3. So in other words, the arithmetic mean of capital A, B, and C is bigger than or equal to the geometric mean of A, B, and C, which is the cube root of A times B times C. And this is true when A, B, and C are positive. So I won't derive that. I think we've done that on the channel before, but that's also a more well-known inequality. Okay, so now we want to apply that with the following choice for A, B, and C. Maybe I'll use my color coding again. Since that's in an orange box, I'll put an orange arrow and then over here to my choice of A, B, and C. So I have the choice of A is, let's see, the square root of x to the x over y to the y. My choice of B is the square root of y to the y over z to the z. And my choice of C is the square root of z to the z over x to the x. Okay, great. So let's see what that'll leave us with. So we can move this 3 up to the other side of the inequality, and we'll have 3 over 2. And then I have to take the product of these three things in the cube root. But then I'll have a square root of a cube root, which is a 6th root. So that'll leave me with the 6th root of the product of the argument of these square roots. So we have x to the x over y to the y times y to the y over z to the z times z to the z over x to the x. But now here's where that magic happens. Notice this x to the x will cancel this x to the x down to the number 1. This y to the y will cancel this y to the y down to the number 1. And then finally, this z to the z cancels this z to the z down to the number 1. So all in all, this entire object just becomes the number 1, which puts our 3 halves on the correct side of our inequality. And now reading this from the left to the right, we see that we have in fact established our inequality. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.